In Chapter 11, Section 5, we are concerned with planes in space. This slide illustrates a property of planes in terms of all the points that lie in the plane, as well as a vector that is normal to the plane. A vector that is normal to the plane is normal to every single other vector that's in the plane. And let's suppose we say n is the normal vector to the plane with components a, b, c, then we are given a point P and give with coordinates x1, y1, and z1. And Q is a general point, which would represent all of the points on the plane. Then the normal vector dot with a PQ vector is going to equal 0 because that's the property of the normal to a plane. It's going to be orthogonal to all the PQ vectors in the plane. So if the normal vector has components a, b, c, then the PQ vector can be found by taking the initial point minus the terminal point. I'm sorry, the terminal point minus the initial point. You come up with the q x minus x sub 1, y minus y sub 1, and z minus z sub 1. And the point P has the coordinates x1, y1, z1, and the point Q is the general point that represents all the points on the plane with coordinates x, y, z. So to find PQ, you take the terminal point and subtract the initial point, and the components are given here. Now, to find the dot product, you multiply the corresponding components and add the results together. And we can see that this is a brand new equation. It's no longer a vector. It does represent the dot product of the two vectors that equals 0. This is a standard equation that we will be able to use to find the equation of a plane in space. The two things you need in order to find the equation of a plane, you need a single point that's on the plane, and you need a vector that is normal to the plane. So if you have those, you can use this equation here to determine the equation of the plane. This theorem is the standard equation of a plane in space, as I mentioned on the previous slide. As long as you have a point, x1, y1, z1, and a normal vector with components a, b, c, you can plug those values into this equation to come up with the equation of the plane. Then the equation that's shaded in blue here is found by distributing the a, b, and c and combining those constants into a single constant d to get the general form of the equation. Find the general equation of the plane containing the points 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. As I mentioned before, you need two things to find the equation of the plane. You need a point, and you need a normal vector. In this example, we're given 3 points altogether. We can pick one of those, but we need to determine a normal vector. To obtain the normal vector, we have these 3 points given here. We can find a vector from the point 2, 1, 1 to the point 0, 4, 1 and to the point negative 2, 1, 4. Let that be vector u and vector v. Those are both vectors in the plane. We want to find a vector that is orthogonal to the plane, and a vector that would be orthogonal to the plane would be orthogonal to both u and v. Now recall, there is a vector that is orthogonal to two other vectors, and that vector is the cross product. So let's find the vectors u and v, find the cross product of those, and that's going to represent our normal vector. So the components of u are negative 2, 3, 0, and to find u, we're starting at 2, 1, 1 and ending at 0, 4, 1. Find those values. The components for u and the components for v are negative 4, 0, 3. The normal vector is the cross product of those two vectors, and you can determine the cross product using the cofactor expansion to get the normal vector 9i plus 6j plus 12k. So now you have your 3 points and you have a normal vector. You select any one of those points and as your x1, y1, z1, and choose 9, 6, 3 as your components for your normal vector and plug that into the formula. Alright, so we'll use the first point 2, 1, 1 as your x1, y1, z1, and we'll use 9, 6, 12 as our ABC. We're going to plug it into this form here and simplify the result. As it's shown here, that's our standard form. Now if you distribute the coefficients and simplify, you get the general form for the equation of the plane. Okay, it can be further simplified, as you can see here, that all of the terms, the coefficients, and the constants are divisible by 3, so you can further simplify it by dividing by 3. Here's another equation that I'd like you to work through, which is very similar to the one we just did. Find the equation of the plane containing the points 2, 3, negative 2, 3, 4, 2, and 1, negative 1, 0. Let's begin by finding a vector u. Let's label our points. We can label them P, Q, and R. Let's find vector u, which it would be a vector from P to Q, and take the terminal point minus the initial point to determine the components. 3 minus 2 is 1, 4 minus 3 is 1, and 2 minus negative 2 is a positive 4. So that's a vector in the plane. We'll call that vector u. And let's find another vector v, which would be from the point P to R. Find the components of the v vector by taking the terminal point and subtracting the initial point. 1 minus 2, we get negative 1. Negative 1 minus 3 is negative 4. And 0 minus a negative 2 is positive 2. So those are both vectors in the plane. To find the normal vector to the plane, we want to find the cross product, which is orthogonal to both of these. So let's find the cross product of the u and v vectors. Okay. Now when you work through that, you can use the determinants. You can take 2 minus negative 16 to get 18. The middle term is opposite of 2 minus a negative 4. Sorry. 2 minus negative 4, that will be a negative 6. And the last component is negative 4 minus a negative 1, and that's going to be our negative 3. So that's our normal vector, and the components of the normal vector we're using A, B, and C. So as long as we have a normal vector and a point, we'll use point P, 2, 3, negative 2, to be our values for x sub 1, y sub 1, and z sub 1. So the general form for the equation of a plane is found by taking the dot product of the PQ vector with the n vector, and simplified, that ends up looking like a times the quantity x minus x sub 1 plus b times the quantity y minus y sub 1 plus c times the quantity z minus z sub 1 is equal to 0. Let's fill in the values that we have found for our normal vector and our point P to find 18 times the quantity of x minus 2 minus 6 times the quantity of y minus 3 minus 3 times the quantity of z plus 2 equals 0. Okay. That's one way to represent the equation of the plane. When you distribute and simplify the terms, you can find that the equation can also be written as 18x minus 6y minus 3z minus 24 equals 0. And it can be further simplified by dividing all of these by 3 to get 6x minus 2y minus z minus 8 equals 0.